Hello, everyone. Welcome back. This is again about improving AI through or with deep learning. So, this is from the Dummy's book, chapter 7, and it's about improving AI. What we have had so far, let's look at it very quickly. So, we introduced the topics, introducing the difference between AI, machine learning, deep learning, and then shaping neural networks, mimicking the learning brain. These topics we have covered. Let's look at more what we have. So, introducing deep learning and detecting edges and shapes from images. All right, so let's see a quick summary about AI, machine learning, and deep learning. Actually, AI is the overarching concept of smart machines. So, AI is the large topic, and the subtopic is machine learning, and from that again, another subtopic is deep learning. So, deep learning is actually a powerful machine learning technique using deep neural networks for complex tasks. Then we went into the details about the neural networks. So let's see just a few things about it. You see here nucleus, dendrites, axons, synaptic terminals, and synapses as well, chemical signals and electrical signals. Then we continued with the connectivist here, and we draw some layers as well, so input layer and hidden layer and output layer. Once we have done that, after that we also talked about simple neural networks, and then we made up the feed-forward architecture, which is a unidirectional flow. There are no loops, there are no backward connections, so no back propagation as well. Once we finished with this part, we went through the following as well. So iterative learning process, and here back propagation. Remember, the simplest form doesn't include that. And now we continue with introducing deep learning. So this is our next topic. Let's see some details. After backpropagation, the next improvement is neural networks led to deep learning, and research also continued despite the AI winter. And like every development, you can see, so it goes up, it develops very fast, and suddenly it goes down again, and it goes up and down and up and down, and it's normal with most of the technologies, or for most of the technologies you see. Just try to think about it. The first Avatar movie was presented 2008 or something like that. Don't remember exactly, but I remember that at that time 3D movies were the big issue, and now there's nothing more about 3D. Yet, yeah, the technology is interesting, and I can bet with you we will have soon another cycle for 3D, another comeback for 3D movies, just as we had. So the very beginning, it was like 1970s or something like that for 3D movies. Then we had somewhere a bit before 2000 and another hype for 3D, and now it's gonna be here again. Remember also that VR, AR techniques or technologies have no news at all recently, but they had like headlines also around the 2015, 16, 17. Well, that's it. So these cycles come again and again, and we have to talk about that as AI winter in the case of AI, and AI summer maybe, or another hype when it develops faster. So anyway, um, neural networks overcame technical problems such as the vanishing gradient, which limits the dimensionality of neural networks. Developers needed larger neural networks to solve certain problems, so large that creating such a large neural network wasn't feasible in 1980s. That caused the problem of the winter, so that's why the development stopped. Moreover, researchers started taking advantage of the computational development of CPUs and GPUs, so central processing units and graphic processing units as well. Now let's see a little bit more details about gradient, vanishing gradient problems. The vanishing gradient problem is like signals fade through layers due to their chain near zero multiplications. Further layers may stop learning due to weak signal transmission, and this slows or halts learning altogether. The vanishing gradient problem is a challenge in training deep neural networks. The gradients indicate how much a small change in a weight affects the overall error or the overall loss. They tell the direction and magnitude in which the weight should be adjusted to reduce the loss. So, the vanishing gradient problem occurs when you try to transmit the signal through a neural network, and as the signal passes through the layers, it quickly fades to near zero, as I just mentioned before. When this happens, the subsequent neurons stop transmitting the signal through their activation functions. This happens because the neural networks are chain multiplications. Okay, so we talked about these things, and now the new solutions help avoid the problem of the vanishing gradient and many other technical problems, allowing larger deep networks in contrast to the simpler shallow networks of the past. Deep networks are possible thanks to the studies of scholars from University of Toronto in Canada, and so on and so on. And even when they seem to most people to be an old-fashioned machine learning approach, they started to research that. GPUs are now more powerful matrix and vector calculation computing units that speeds up the computations for backpropagation. These technologies make training neural networks achievable in a short time and accessible to more people. Research also opened a world of new applications. Neural networks can learn from huge amounts of data and take advantage of big data such as images, text, transactions, and social media data, creating models that continuously perform better depending on the flow of data you feed them. Now, big players such as Google, IBM, and Meta, and Microsoft spotted the new trend and have since 2012 started acquiring companies and hiring experts in these new fields of deep learning. For example, Yann LeCun, the French scientist who created convolutional neural networks, is vice president and chief AI scientist at Meta. Okay, now understanding deep learning issues. As things stand now, people have an unrealistic idea of how deep learning can help society as a whole. You see, a deep learning application beat someone at chess or Go and think if it can perform that truly amazing task, what other amazing things can it do? The problem is that even its proponents don't fully understand deep learning. In technical papers about deep learning, the researchers often describe layers and nebulous processing organized into a network with no sort of discourse into what really happens in each of those boxes. So anyway, the essential point to remember is that deep learning doesn't understand anything. It uses a massive number of examples to derive statistically based pattern matching using mathematical principles. When an AI wins a game involving a maze, it doesn't understand the concept of a maze. It simply knows that certain inputs manipulated in specific ways create certain winning outputs. In contrast to human, deep learning must rely on a huge number of examples to discover specific relationships between input and outputs. When learning something new, deep learning requires special training to accomplish the task. And it would be easy to fool because examples beyond its training data may not be recognized. Humans can and also create hierarchies of knowledge without any sort of training. We know, for example, without much effort, that dogs and cats are both animals. In addition, in knowing that dogs and cats are animals, a human can easily make a leap to see other animals as animals, even with no specific training. Deep learning would require separate training for each thing that is an animal. In short, deep learning cannot transfer what it knows to other situations as humans can. And even if with these limitations, deep learning is an amazing tool, but it should not be only tool in the AI toolbox. Using deep learning to see patterns where humans can't is the perfect way to apply this technology. Patterns are an essential part of discovering new information. And for example, human testing of compounds or to battle the cancer or fight coronavirus pandemic could take an immense amount of time. And by seeing the patterns where humans can't, deep learning could make serious inroads toward a solution with a lot less effort than humans would require. Okay, deep learning may seem to be a larger neural network that runs on more computers. So see here again, deep learning needs a huge data. Deep learning cannot generalize knowledge across contexts. And deep learning is easy to fool, this as I mentioned before. Humans against deep learning, so humans build abstract hierarchies naturally, as you saw between with the animals, cats and dogs. And then deep learning requires explicit training for each category, and humans can transfer knowledge. Unlike deep learning cannot do that. powerful but limited tool should not be limited to AI toolbox. Right, now let's see more. So when you look inside deep learning, you may be surprised to find a lot of old technology, but amazingly, everything works as it never has before. Because researchers finally figured out how to make some simple, good old solutions work together and big data can automatically filter, process, and transform data. For instance, new activations like RE, LU aren't all that new. They've been known since the perceptron as well. So anyway, thing is that now even old technologies became emergent and developed in that way, and that's why now they work together the best. Also, CNNs were discovered not now, but 1980s by LeCun, mentioned before as well, LeCun. Such networks now bring apps about astonishing results because they use many neural layers and lots of data. Big data enabled this technology. The same goes for technology that allows a machine to understand human speech or translate from one language to another. It's decades-old technology that a researcher revisited and got to work in that new deep learning paradigm. Of course, part of the difference is also provided by data. More about this topic we can see later as well. Now, increased usage of GPU allowed us to process data faster. And also computer networks allow us to have this huge data together, this huge data. Anyway, together with parallelism, so more computers put in clusters and operating in parallel, GPUs allow you to create larger networks and successfully train them on more data. In fact, GPU is estimated to perform certain operations many times faster than we used as well, CPU, so faster than GPU, allowing a cut in training times for neural networks from weeks to days. GPUs aren't the only option for building effective deep learning solutions. Promptly, special application specific integrated circuits, so ASICs, you see here, specialized hardware chips designed for a single specific task like Bitcoin mining, unlike general purpose like CPU and GPU. Have made appearance, and the designers have demonstrated that those circuits performs even better than GPUs. For instance, in 2015, Google started developing a tensor processing unit, so TPU, you see here as well, for faster training using TensorFlow in the cloud. So blazing fast, application-specific integrated circuit to accelerate the calculations involved in deep learning when using Google specialized computation library, so-called TensorFlow. In 2018, Google made TPUs available in its cloud centers as well. Now, TPUs are not general purpose like CPUs and GPUs, just as ASICs, but excel at accelerating large-scale AI workloads. Okay, so a turning point in AI driven by technical innovation, hardware evaluation, big data availability happened, and through that, deep learning was enabled. Still limited, but incredibly powerful when you use it in the right way. Now we come to the next topic, finding even smarter solutions. So here, deep learning influences AI's effectiveness in solving problems in image recognition, machine translation, and speech recognition that were initially tackled by classic AI and machine learning. In addition, it presents new and advantageous solutions, such as continuous learning using online learning, and then reusable solution using transfer learning, then simple straightforward solutions using end-to-end learning, and then more democratization of AI using open source frameworks. So we talk about these four approaches now. We start with using online learning. Neural networks are more flexible than other machine learning algorithms, and they can continue to train as they work on producing predictions and classifications. This capability comes from optimization algorithms that allow neural networks to learn, which can repeatedly work on small samples of examples called batch learning, or even on one example at a time called online learning. So we differentiate between batch learning and online learning here. Deep learning networks can build their knowledge step by step and be receptive to new information that may arrive, like, for example, like baby's mind, which is always open to new stimuli and learning experiences. For instance, a deep learning application on a social media website can be trained on cat images. As people post photos of cats, the application recognizes them and tags them with an appropriate level. So, label. When people start posting photos of dogs on the social network, the neural network doesn't need to restart training. It can continue by learning images of dogs as well. This capability is particularly useful for coping with variability of internet data. A deep learning network can be open to novelty and adapt its ways to deal with it. So we continue now with transfer learning. Flexibility is handy even when a network completes its training, but you must reuse it for purposes different from the initial learning. Networks that distinguish objects and correctly classify them require a long time and a lot of computational capacity to learn what to do. Extending and expanding a network's capability to new kinds of images that weren't part of the previous learning means transferring the knowledge to this new problem, that is the transfer learning. For instance, you can transfer a network that's capable of distinguishing between dogs and cats to perform a job that involves spotting dishes of macaroni and cheese. You use the majority of the layers of the network as they are, so you freeze them, and then work on the final output layer fine-tuning, thus adapting existing neural network to perform a new task. Recent advances have even made it possible to fine-tune all layers of a deep learning network to obtain better results. Low rank adaptation, that is LoRa, so low rank adaptation is a new technique that leverages matrix multiplication to adapt an entire network using the least number of computations possible. In a short time, and with fewer examples, the network will apply to macaroni and cheese whatever it learned in distinguishing dogs and cats. It will perform even better than a neural network trained only to recognize macaroni and cheese. Transfer learning, a concept new to most machine learning algorithms, opens a possible market for transferring knowledge from one application to another, from one company to another. Google, Meta, and Microsoft are already doing this, actually sharing the immense research work by making public many of the networks they built. This is the step in democratizing deep learning by allowing everyone to access its potentiality. We continue with using open source frameworks as well. Yes, so you see here democratization of AI to save time and resources. Here you have it. Training from scratch, transfer training. Training from scratch takes much more time than transfer learning. Okay, so open source frameworks. Today, networks can be accessible to everyone, including access to tools for creating deep learning networks. It's not just a matter of publicity and publicly divulging scientific paper explaining how deep learning works. It's a matter of programming. In the early days of deep learning, you had to build every network from scratch as an application developed in a language such as C++, which limited access to a few well-trained specialists. Scripting capabilities today, so for instance, using Python, are better because of a large array of open source deep learning frameworks such as TensorFlow by Google are available. So these frameworks allow the replication of the most recent advances in deep learning using straightforward commands. Along with many lights come also shadow. So neural networks need huge amounts of data to work, and data isn't accessible to everyone because larger organizations hold it. Transfer learning can mitigate the lack of data, but only partially because certain applications do require actually data. So actual data, so most recent data. Consequently, the democratization of the AI is very limited as well. Now, also, deep learning systems require huge computational resources and are so complex that their outputs are both hard to explain and frail because tricks can fool those systems very easily. Bias is also there included. Any neural network can be sensitive to adversarial attacks. So again, adversarial attacks which are input manipulations devised to deceive the system into giving a wrong response. Here you see the attack, adversarial attack. Now, the next stage is end-to-end learning. So we arrive to end-to-end learning, which means that it solves problems in an easier and more straightforward way than previous deep learning solutions, and might therefore have more impact when solving problems. Okay, so say that you want to solve a difficult problem, such as having AI recognize known faces or drive a car. Using the classical AI approach, you would have to split the problem into more manageable subproblems to achieve an acceptable result in a feasible amount of time. For instance, you wanted to recognize faces in a photo. Previous AI systems arranged the problem into the following parts: find the faces in the photo, crop the faces from the photo, process the cropped faces, to have a pose similar to an AI, similar to an ID card photo, and feed the processed cropped faces as learning examples to a neural network for image recognition. Today, you can feed a photo to a deep learning architecture and guide it to learn to find faces in the images and then classify them. You can use the same approach to find faces in the images and then classify them. Sorry. You can use this. So one more time. Today you can feed the photo to a deep learning architecture and guide it to learn to find faces in the images, and you can also use the same approach for language translation, speech recognitions, even for self-driving cars as well. Detecting edges and shapes from images, and now this is interesting. If we go into that, here we have it. So end-to-end learning, useful for face recognition, translation, self-driving. And you see here computer features phenomenon. So basically traditional model, and here you see the end-to-end model as well. Okie dokie. So detecting edges and shapes from images. Convolutional neural networks, also CNNs, have fueled the recent deep learning renaissance, so the deep learning development. Practitioners and academics are persuaded that deep learning is a feasible technique because its results in image recognition or tasks are excellent. This success has produced a sort of gold rush, with many people trying to apply the same technology to other problems as well. So let's talk about them. Okay, now CNNs are no new idea again. They appeared, as we mentioned already, in the 1980s by LeCun, so we have seen that before. At the time, having a machine able to decipher handwritten numbers was quite a feat, so quite interesting, fantastic. One that assisted the postal service in automating zip code detection and sorting incoming and outgoing mail. Okay, so now you can see here an example of that from 1980s. Please understand, it's like 40 years ago, right? So yes, that was that time very interesting and very new for everyone. Developers achieved some results earlier by connecting a number of images to a detection neural network. In their attempt, each image pixel was connected to a node in the network. The problem with this approach is that the network cannot achieve translation invariance, which is the capability to decipher the number under different conditions of size, distortion, or position in the image, as you see also later, which we look at now. Where is it? Here. Now, convolution. Wait, where are we now? Okay, here we go. So, originated with Lennart 5, right? Used for reading zip codes, just as mentioned before, and translation invariance is the following. So, capability to decipher the number under different conditions of size, distortion, and or position in the image. Also, it made many mistakes. The problem of translation invariance is the following. So, early models failed to handle variations in position and scale, required manual image transformations, so feature engineering, such as resizing, moving, and cleaning the pixels, and creating special chunks of information for better network processing. CNN was the game changer here. Due to CNN, things developed quickly. So convolutions easily solve the problems of translation invariance because they offer a different image processing approach inside the neural network. Convolutions, which are the foundation of Lennart 5, provide the basic building blocks for all actual CNNs, performing the following tasks. Image classification, so determining what object appears in an image. Image detection, finding where an object is in an image. Image segmentation, separating the areas of an image based on their content. For example, in an image of a road, separating the road itself from the cars on it and the pedestrians on it. Just as mentioned before, so convolutions came to rescue. This problem and automatically detecting edges, curves, and patterns here, and maintaining position invariance across images. Okay, now let's think about it, how it works. To understand how convolutions work, you start from the input, which is an image composed of one or more pixel layers called the channels. Using values from 0 to 255, so 0, the pixel is fully switched on, and 255, the pixel is fully switched off. For instance, RGB, so red, green, and blue, right? Images have individual channels for red, green, and blue colors. Mixing these channels generates the palette of colors as you see them on the screen. The input data receives simple transformations to rescale the pixel values. So for instance, to set the range from 0 to 1, and then pass on those values. Transforming the data makes the convolutions work easier because convolutions are simply multiplications and summation operations And then the convolution neural layer takes a small portion of the image, multiplies the pixel values inside the portion with by a grid of particularly devised numbers, sums everything derived from the multiplication, and projects it into a next neural layer. Such an operation is flexible because backpropagation forms here refines the filters to recognize features, so forms the basis for numeric multiplication inside a convolution, and the values that the convolution filters are image characteristics which are important for the neural network to achieve its classification task. Some convolutions catch only lines, so from lines to textures, and curves and special patterns, and then no matter where they appear in the image, and they get the entire objects as well. Okay, so the deeper it is, the more it has to be abstracted. Again, image processing tasks, so classification, what is in the image, detection, where is the object, segmentation, what region does the object occupy. So here, segmentation, where what region is occupied, then here classification, localization, so what is in the image, a cat. Here again, object detection, dog, cat, so multiple objects are here, and the segmentation where they are. As we mentioned before, 0 to 255, and we got the RGB images from that. And we also talked about the input data receive simple transformations and then pass those values. So backpropagation forms the basic of numeric multiplication inside the convolution. The values that the convolution filters are image characteristics, which are important for the neural network to achieve its classification. Some convolutions catch only lines, others can also up to images. So here I have 2 YouTube links to share with you. Let's look at them.
Okay, pop quiz. What am I drawing? I'm going to make 3 predictions here. Firstly, you think I drew a house, you'd be right. Secondly, that it just came really easily to you, it was effortless. And thirdly, you're thinking that I'm not much of an artist. And you'd be right on all counts there. But how can we look at this set of geometric shapes and think, oh, house. If you live in a house, I bet it looks nothing like this. Well, that ability to perform object identification that comes so easily to us does not come so easily to a computer, but that is where we can apply something called convolutional neural networks to the problem. Now, a convolutional neural network, or a CNN, is an area of deep learning that specializes in pattern recognition. My name is Martin Keane, and I work in the IBM garage at IBM. Now, let's take a look at how CNN works at a high level. Well, let's break it down. CNN, convolutional neural network. Well, let's start with the artificial neural network part. This is a standard network that consists of multiple layers that are interconnected, and each layer receives some input, transforms that input to something else, and passes it as output to the next layer. That's how neural networks work. And CNN is a particular part of the neural network, or a section of layers. Let's say it's these 3 layers here. And within these layers, we have something called filters. And it's the filters that perform the pattern recognition that CNN is so good at. So let's apply this to our house example. Now, if this house were an actual image, it would be a series of pixels, just like any image. And if we zoom in on a particular part of this house, let's say we zoom in around here, then we would get, well, the window. And what we're saying here is that a window consists of some perfectly straight lines. Almost perfectly straight lines. But you know, a window doesn't need to look like that. A window could equally kind of look like this, and we would still say it was a window. The cool thing about CNN is that using filters, CNN could also say that these two objects represent the same thing. The way they do that then is through the application of these filters. So let's take a look at how that works. Now, a filter is basically just a 3x3 block. And within that block, we can specify a pattern to look for. So we could say, let's look for a pattern like this, a right angle in our image. So what we do is we take this filter, and it's a 3x3 block here. We will analyze the equivalent 3x3 block up here as well. So we'll look at, first of all, these first group of 3x3 pixels, and we will see how close are they to the filter shape. And we'll give that a numeric score. Then we will move across one column to the right and look at the next 3x3 block of pixels and score how close they are to the filter shape. And we will continue to slide over or convolve over all of these pixel layers until we have mapped every 3x3 block. Now that's just for one filter, but what that will give us is an array of numbers that say how closely an image matches our filter. But we can add more filters. So we could add another 3x3 filter here, and perhaps this one looks for a shape like this. And we could add a third filter here, and perhaps this looks for a different kind of right angle shape. If we take the numeric arrays from all of these filters and combine them together in a process called pooling, then we have a much better understanding of what is contained within this series of pixels. Now that's just the first layer of the CNN. And as we go deeper into the neural network, the filters become more abstract, or they can do more. So the second layer of filters perhaps can perform tasks like basic object recognition. So we could have filters here that might be able to recognize the presence of a window, or the presence of a door, or the presence of a roof. And as we go deeper into the CNN to the next layer, well, maybe these filters can perform even more abstract tasks, like being able to determine whether we're looking at a house, or we're looking at an apartment, or whether we're looking at a skyscraper. So you can see the application of these filters increases as we go through the network and can perform more and more tasks. And that's a very high-level basic overview of what CNN is. It has a ton of business applications. Think of OCR, for example, for understanding handwritten documents. Think of visual recognition and facial detection and visual search. Think of medical imagery and looking at that and determining what is being shown in an imaging scan. And even think of the fact that we can apply a CNN to perform object identification for badly drawn houses. If you have any questions, please.
If this works. So very quickly, just let's take a look at this one here as well.
To support the production of more high-quality content, consider supporting us on Patreon or YouTube membership. Additionally, consider visiting our parent company, the Convolutional Neural Network. For our discussions on convolutional neural networks, we will go with a very common example, number recognition. The reason this example was chosen is because of this great interactive resource by Adam Harley, a robotics PhD at Carnegie Mellon University. I have linked the resource in the description so that you too can experiment with it and see the internals of a convolutional network. Now, if you can recall from our example on an image pattern recognizer using a feed-forward network, we set up an idealized system and made the assumption that each hidden layer in our network would build upon further layers of abstraction, from vertical lines to combinations of vertical lines. However, in actuality, as we explained, this wouldn't happen, and the receptive fields in the network would be a lot more random to the human eye due to the architecture of feed-forward networks and how they compute. With convolutional networks, however, this isn't the case, and we could to some extent see these layers of abstraction building up. Before we delve into why and how this happens, let's first set up a structure for the network we will be using. As with our previous example in image recognition, the input will be the individual pixels of our image, and the output the patterns we are trying to classify. In this example's case, we have 10 outputs, numbers 0 to 9. For the layers in between, we will have 2 convolutional layers, 2 pooling layers, and 2 fully connected layers. Now that was a lot of new terminology thrown around, so let's break it down layer by layer, starting with the input. While we have already stated that the input is the individual pixels of the image, I want to mention some important details about how a computer views this image. Every image in a digital device is stored as a matrix of pixel values. This is referred to as a channel, a certain component of an image. Now with a typical digital camera, every image will have 3 channels, red, green, and blue, RGB, which you can imagine as 3 2D matrices stacked upon one another. For the sake of simplicity, we will assume our input has just one channel, the luminance of the image, with the value of each pixel represented in 8 bits. In other words, the pixel values will range from 0 to 255, with 0 indicating dark or transparent luminance, and 255 is bright. As a side note, digital systems store all types of sensor data and other information in this fashion. For example, for a convolutional network that would operate on speech, we could represent that speech as a matrix of frequency values. Coming back on topic, now that we understand the format of the input, let's finally delve into where the real magic happens, the convolutional layer. As you can assume, this layer and the network as a whole get their names from the convolutional operator, which in layman terms is the mathematical combination, in other words the dot product of 2 functions to produce a third function. In CNNs, this operation is implemented in what is referred to as a feature detector, filter, or most commonly, a kernel. You can think of a kernel as a mini matrix, orders of magnitude smaller than the input. In a convolution operation then, the kernel moves across the input image, taking the dot product of the 2 matrices and then saving the values to a new matrix, dubbed the feature map of the original image. At this point, you may be wondering how this is able to detect any features at all. Well, if a kernel is initialized with the values in a specific configuration, they can be used to transform an input image and find various patterns. Take these kernels for instance, when loaded with the appropriate values and convolved with the input image, produces an output which highlights various edges in the photo. Now I won't delve into the specifics of the various types of kernels in this video, but there are many resources that talk about them extensively, such as Computerphile and their various videos on kernels like the Sobel edge detector. Coming back on topic, as you can see, kernels are essentially ways to do fast computation and produce a new output. In this case, we're doing it with an image, with an effect or features highlighted. Programs like Photoshop use these simple kernels for effects like blurs, for instance. Now when we look at a typical image, take in how much is actually going on. There are various edges, shapes, textures, etc. that stack together to make various objects and the overall image we are looking at. At the start of a convolutional network, the types of kernels we'd use would be quite simple and more geometric, detecting things such as edges, corners, and simple shapes and patterns, like a circle for instance. Additionally, each convolutional layer can have multiple kernels that produce multiple feature maps of their own. So for our example, we can see that our first layer has 6 kernels, and these kernels are detecting simple patterns like horizontal lines, vertical lines, and corners on our drawn numbers. As a side note, for each of the convolved pixels in our feature map, a nonlinearity function was also applied, in this instance a ReLU. We discussed this function in previous videos and the need for nonlinearity in neural networks, so our feature maps are more adaptable to real-world data. Also, you can now see how complicated this process would become if we had more than one channel, as each channel would have 6 feature maps, in this instance leading to 18 for an RGB image, and then those feature maps would have to be filtered together or operated on separately depending on your specifications. For instance, in a self-driving system, a red hexagon is a stop sign, so we would need separate channels and kernels for those channels. However, coming back to our example, just one channel, luminance, is more than enough. Moving on, now that we have a rectified feature maps, the next layer in CNNs after the convolution is a pooling layer. Pooling layers are used to downsample our feature maps, keeping the most important parts and discarding the rest, and primarily done to reduce the overfitting rate, and so that calculations can be sped up in later layers due to the reduced spatial size of the image. The type of pooling our network implements is max pooling, in which we take another kernel and slide it across our input feature maps, and the largest pixel value in that region is what is saved to our new output feature map.
So here let's stop because the convolutional network layer was explained completely. We don't go deeper right now. But if you are interested, you can see these files by yourself as well. So you can see these videos by yourself. All right, now here again, as the image data passes through various convolutions, it's transformed, assembled, and rendered in increasingly complex patterns until the convolution produces reference images as well. So here again, LANET 5, 1980s, you remember. So we move on, and we have 2 winter cycles here, and now we arrived at this stage where we are, and there are rise of alternatives like SVM as well. So support vector matrices, right? Okay, let's see. The next one is the ImageNet breakthrough. So in 2006, the effort by Fei Li was seen, and then the computer science professor at the University of Illinois, Urbana-Champaign, to provide more real-world data sets to better test algorithms. She started amassing an incredible number of images representing a large number of object classes. She and her team achieved this monumental task by asking people on the internet to complete microtasks like classifying an image for a small fee. The resulting dataset completed in 2009 was called the ImageNet and contained 3.2 million labeled images arranged into 5,247 hierarchically organized categories. You can learn more about this dataset if you want, if you get into imagenet.org. And ImageNet soon appeared at a 2010 competition in which neural networks provided their capability to correctly classify images arranged into exactly 1,000 classes. In 7 years of competition, the winning algorithms raised the accuracy in predicting the images from 71.8% to 97.3%, which surpasses human capabilities as well. So yes, humans make mistakes in classifying objects. At beginning, researchers noticed that their algorithm started working better with more data. There was nothing like ImageNet at that time. And then they started testing new ideas and improved neural network architectures that brought about a host of innovations in the way to process data, build layers, and connect them all together. Striving to achieve better results on the ImageNet competition had favorable impacts on all related fields of deep learning researches. Also, the ImageNet competition no longer take place. Researchers are even today developing more CNN architectures, enhancing accuracy or detection capabilities as well as robustness. Okay, in fact, many deep learning solutions are still experimental and not yet applied to critical applications such as banking or security, not just because of the difficulties in their interpretability, but also because of vulnerabilities. Vulnerabilities come in all forms. So researchers have found that by adding specially devised noise or changing a single pixel in an image, a CNN can radically change its answers in attacks that are not targeted or targeted. So not targeted would be just need to fool the CNN, or you want the CNN to provide a specific answer. The point is that CNNs aren't the safest technology yet. You can simply use them in place of your eyes. You have to take great care of them. And you see here as well, Panda, the confidence is really high. You take a little bit of noise and then the Panda will be changed to a gibbon out of a sudden. Also for this I have a nice video you can see here, so let's see that.
Károly Zsolnai Fehér. This will be a little non-traditional video where the first half of the episode will be about a paper and the second part will be about something else. Also a paper. Well, kind of. You'll see. We've seen in the previous years that neural network-based learning methods are amazing at image classification, which means that after training on a few thousand training examples, they can look at a new, previously unseen image and tell us whether it depicts a frog or a bus. Earlier, we have shown that we can fool neural networks by adding carefully crafted noise to an image, which we often refer to as an adversarial attack on a neural network. If done well, this noise is barely perceptible and, get this, can fool the classifier into looking at a bus and thinking that it is an ostrich. These attacks typically require modifying a large portion of the input image, so when talking about a later paper, we were thinking, what could be the lowest number of pixel changes that we have to perform to fool a neural network? What is the magic number? Based on the results of previous research works, an educated guess would be somewhere around 100 pixels. A follow-up paper gave us an unbelievable answer by demonstrating the 1 pixel attack. You see here that by changing only 1 pixel in an image that depicts a horse, the AI will be 99.9% sure that we are seeing a frog. A ship can also be disguised as a car, or, amusingly, with a properly executed 1 pixel attack, almost anything can be seen as an airplane by the neural network. And this new paper discusses whether we should look at these adversarial examples as bugs or not, and of course does a lot more than that. It argues that most datasets contain features that are predictive, meaning that they provide help for a classifier to find cats, but also non-robust, which means that they provide a rather brittle understanding that falls apart in the presence of adversarial changes. We are also shown how to find and eliminate these non-robust features from already existing datasets, and that we can build much more robust classifier neural networks as a result. This is a truly excellent paper that sparked quite a bit of discussion. And here comes the second part of the video with the something else. An interesting new article was published within the Distill journal, a journal where you can expect clearly worded papers with beautiful and interactive visualizations. But this is no ordinary article. This is a so-called discussion article where a number of researchers were asked to write comments on this paper and create interesting back and forth discussions with the original authors. Now, make no mistake, the paper we've talked about was peer-reviewed, which means that independent experts have spent time scrutinizing the validity of the results, so this new discussion article was meant to add to it by getting others to replicate the results and clear up potential misunderstandings. Through publishing 6 of these mini-discussions, each of which were addressed by the original authors, they were able to clarify the main takeaways of the paper and even added a section of non-claims as well. For instance, it's been clarified that they don't claim that adversarial examples arise from software bugs. A huge thanks to the Distill journal and all the authors who participated in this discussion, and Ferenc Huszár, who suggested the idea of the discussion article to the journal. I'd love to see more of this, and if you do too, make sure to leave a comment so we can show them that these endeavors to raise the replicability and clarity of research works are indeed welcome. Make sure to click the link to both works in the video description and spend a little quality time with them. You'll be glad you did. I think this was a more complex than average paper to talk about. However, as you have noticed, the visual fireworks were not there. As a result, I expect this to get significantly fewer views. That's not a great business model, but no matter, I made this channel so I can share with you all these important lessons that I learned during my journey.
Lessons learned during the journey. Here we also finish our journey. With our panda gibbon, because the next slide would be about Q&A, which we don't have right now here. Again, I'm very pleased to share with you this, and I'm very happy that you also paid attention to this lesson or class. Thank you very much, and see you then again during the class time. Bye.